Good morning, everyone. I hope all are doing well. And today we have a webinar on Introduction to Quantum Computing. And first of all, I really welcome everyone for this session. And today we have a special guest. She's Trapti Kalra. So before we get into our webinar, I would like to quickly, welcome our guest and have a quick introduction about our guest. Trapti, welcome to our webinar. You're on mute.
Hi everyone. Good morning.
Good morning and welcome, Tripti, for the Times for AICOE events. Thank you for your time for this webinar, and we are really happy to have you on this webinar. And to give for all our attendees, to give you a quick introduction, Tripti is an AI leader and currently working at IBM, and she has more than 23 plus years of work experience. And as you can see in my screen, she's a very well master in AI, applied AI and generative AI, as well as automation. And she carries her interest in various domain like quantum ML solution, and she's also been a researcher in these areas. And she's also have been an applied technical skills experience to solve multiple problems. And also she has a global leadership position leading teams, vendors, and also she is an advisory to her different clients. And also she has done many of automation at AI, ML, IT strategy, transformation programs, and work closely with AI startups. And also her top skills are she's a learner and practitioner in quantum computing and machine learning, and she's also been an expert in AI domain. And there is I cannot keep on explaining, because she is very well experienced. She has a vast experience in different AI and ML domain. So, and today we have a very interesting topic, that is introduction to quantum computing. And Tripti, being a learner and practitioner, she will be able to give us a quick insight about what is a quantum computing and how it is creating impact in the current industry trends. So Tripti, I will not take much time. So over to you.
Okay, sure. Can you confirm that you're able to see my screen and
Yes,
hear
yes, 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 I can see your screen.
Okay. Okay, then. Okay, so thanks for the introduction. Basically, I'm a learner. I enjoy learning. So that's in summary explain some of the skill sets that I try to practice. So what I'll try to do today is I'm trying to familiarize yourself with quantum computing, give you some of the basics about quantum computing, what are the essential ideas you need to know, and then how do we realize a quantum computer, a bit of idea about that, what the future is looking like. Then most importantly, in this session, why are we learning about quantum computing? So some use cases, how this domain of quantum computing applies to different industries. So we'll be talking on a few of those things. Now, what the way I'll try to leverage the 1 hour is, I will try to break logically at intervals and take questions, though we will have a dedicated Q&A time towards the end. So if there are any quick questions which are troubling you, you should ask them in between. Otherwise, we can do a detailed Q&A later. So should I start now?
Yes.
Yeah. Okay. So, you know that first is why should we know about this topic? We already have, supercomputers, the classical computers. So this new paradigm of quantum computing, that's because, there are big problems which are still unsolved in our environment. And I'll just try to motivate you for some of them. So some of the unsolved big problems in our world are problems like creating ammonia for generating fertilizers. I don't know how many of you know, but almost 1 to 2% of total energy that we produce on the planet is used just to create these synthetic fertilizers to meet the food supply demands of our planet. And this is a quite a you can say energy consuming process, nitrogen fixation. And the process was discovered sometime in the 1950s. It's called the Haber process. And in this process, the challenge is to process the nitrogen to create ammonia molecule. For that, the problem is that can we discover better catalysts or improve the process somehow? And this is a chemical problem which we have not been able to solve even with all the classical computers. That's because it's very difficult. And I'll show you how we really have to uh, work on this problem and how quantum, something like quantum, could be a solution to it. Similarly, we have other problems like to make CO2 conversion into hydrocarbons more efficient, new catalysts need to be discovered. There are a lot of opportunities to come up with better financial models to manage our global economies, given so many variables that we have around the different moving, different impacts. There is no economic model which can actually predict with some good predictability what will be the stability of economy. So that's why there's always this low accuracy in predictions for any kind of financial model. And one of the reason is we always constrain the problem given the capacity of the computers that we have at hand. But if we had a model where we could actually stimulate a lot of scenarios, chances are we could come up with better financial models. Another application in the medical area is that still in medical, while we've made a lot of advances, there's still so many problems around some diseases like cancer, like multi-drug resistant bacterial issues, which are not getting resolved today because we don't have enough medicines. Given the number of chemicals and elements that we have around, we know there could be new classes of antibiotics, but the process of drug discovery and coming up with new molecules is very time consuming. It takes years and years and a lot of experimentation, very high cost, and therefore the motivation to solve some of these problems is low. Or even if there's motivation, it takes a lot of compute resources, a lot of you can say human resources, and of course all the equipment, the animals on which we experiment to come up with these solutions. But think about a situation where we could actually just you can say compress all of this together, right? Like just reduce the time and the cost and the labor and have more digital based experiments. The classical computers cannot solve this problem. So even the world's most powerful supercomputer, if you look at it, which is it's called the Summit quantum computer, which is very powerful, even with that there are still problems which are intractable. So there are problems which just by due to the sheer nature of the problems, we can address them classically. There are problems that we cannot address today. There are some problems which we do hope to address with quantum. So what kind of problems are these? So the problems which are very, very challenging, like, factoring very large numbers, which is the basis of cryptography and cybersecurity, those fall under the realm of NP-hard problems. However, factoring is one problem which is easily solvable by a quantum computer, right? So factoring could be one option. There are other problems which are not even NP-hard problems, but they're out of domain, out of the possibility of getting solved by the classical computers. So they are like just simulating quantum mechanics. We won't be touching about quantum physics and mechanics today, but think about being able to simulate on a computer some problems in quantum mechanics for better discoveries. So that is something which we can do easily on a quantum computer because it is easy to simulate that behavior when the underlying hardware is also mimicking that kind of phenomena, right, on a quantum computer. So that way, the novelty around quantum is actually opening up a lot more avenues to solve problems which we cannot solve today. So that's really the motivation behind why we would want to invest in quantum computing. So let's go on to the basics, right? And after this, I'll break for some questions because this is going to be a bit intensive. So, in a classical computer, we have bits, which I hope you all understand. So, I'm just going to bring the analogy so that you can appreciate how a quantum computer works. So, classical computer has a bit, which is the basic unit of information, and it can take to either of one value, a 0 or a 1. So, it's all about 0 and 1s. That's a bit. Now, how do we manage computation in a classical computer? So that is done by a logical circuit, which consists of a basic set of gates. For example, AND or NAND or XOR. So all these are there. So these gates actually work on the bits to change the state of the bits and drive the computation on the quantum computer. And this is a collection of lot of these logical circuits will realize an algorithm, which we typically code on the computer. In the same way, if we draw the analogy, in a quantum computer, our basic unit of information is a qubit. So QU for the quantum bit. And this is a controllable object. So the same way in which in a transistor we can control the bits, we can give electricity to change the state of a bit from 0 to 1. Similarly, this is controllable qubit, which holds a unit of information. You'll note a difference that instead of representing this as a point, 0 or 1, like two separate values, the quantum is a kind of continuum. So you can think of it that a quantum bit can actually hold information which is anywhere on a sphere. I'm talking about a single qubit. So at the North Pole, what we call is a 0. This is called a ket. The symbol is called a ket, and this is used to represent a quantum 0 state. Okay, just for you to draw the analogy to the bit. And if you look at the South Pole, then this is the other extreme state, which is a quantum 1, which is equivalent to a 1 bit state. So this is called ket 0, this is called ket 1. However, it is important to realize that in a quantum bit, given the quantum properties, the state of a qubit can be anywhere between 0 and 1. So imagine it as being anywhere between on this sphere. It can be anywhere on the sphere at a given point in time. So you can see on a sphere, there are infinite points on the sphere. So it can actually occupy any of the states. And this is just the basic idea of how a qubit differs. So now you can understand that it can hold much more information because it's any proportion of 0 and 1, which will be like, let's say if there's a equal, if the qubit is holding the state where it is 0 and 1 with equal probability, it will be falling somewhere on the equator of this particular globe. So this is where we'll say that, okay, the qubit has a 50% chance of being in 0 and 50% chance on being in one state. So like this, it can have infinite possible states, a single qubit. Now, if you have a lot of qubits, you can imagine that you're getting a lot more states than a bit, classical bit, which would only, at any point in time, it can only hold one state. So this is the power of the quantum computer because it allows you to express problems which have a very large dimension in a limited amount of, you can say, compute. And we will understand a bit more how this actually happens. But similar to what I discussed with you on the classical logic circuit, how do we work with these qubits? So in the same way, we try to simulate quantum circuits, which is made up of a set of quantum gate operations, which work on these qubits or they operate on these qubits. And this is equivalent to the logical classical circuit on a quantum computer. And this actually gives rise to algorithms. Then you connect a lot of quantum circuits together to realize an algorithm which performs an operation which makes some scientific or business sense. Just to familiarize you a little bit with the notations, this is a controlled gate. It's like a 2 qubit gate. these are separate 1 qubit gates. We'll look at them in what these H gates actually do. Q0 means 1 qubit, and this is the name given to the second qubit. So in this circuit, we actually have 2 qubits. Because we don't know the state, we are representing it by a common symbol here. And they are getting, you can say, interrelated by this controlled NOT gate. Then there are some operations which are operating individually on the gates. So we'll understand a little bit more about what is actually happening here. But in the end of the circuit, we are measuring the state of a qubit, and that is depicted by this red symbol. And once we have done the measurement, it tells us what is the state of the final qubit. After performing all these operations, which were again under an algorithm, we are able to then predict what the output is. Okay, so that's the basic idea and how it is equivalent to a classical computer. So as I explained, the qubit is a state of 0 and 1. So the way to represent it mathematically, because we have to be careful about the notation here, we're talking about computation. We can represent the state at any point in time on the sphere as A ket 0 plus B ket 0. It means that a single qubit contains 2 pieces of information. And how can we say 2 pieces of information? The amplitude of being in the 0 state plus the amplitude of being in the 1 state is represented by the numeric values A and B. There is a bit of difference than the normal mathematics that we study. A and B can actually be complex numbers. That's the key idea that you need to understand. And the reason they're on represented as complex numbers, because mathematically, if you see on the sphere, there will be 3 dimensions, and that will result into phases as well. So you have your x-axis, y-axis, and a phase axis. Now, when we measure, what happens is the way the mathematics on quantum computation actually works is when the moment we measure, there are chances that as we measure, the state will collapse or it will come to a stable state which we can observe. So the chances that this will be a 0 state is A square. The probability that it can be in 1 state will be B square. Whenever we measure a qubit, it will become 0 or 1 equivalent to a bit. So all the magic that actually happens is before we measure a qubit, it is interacting with other qubits using the controlled gates and 2 qubit gates or 3 qubit gates or any number of qubit gates. And they are forming some operation on a state of many qubits. When you measure them, all this entire state will collapse into a certain state, which will actually be the result to the problem we are trying to solve. And that's how we extract it in the forms of zeros and ones and convert this into a meaningful result for ourselves. So just to let you know how the gates actually operate on each other, similar to the classical computers, we have a NOT gate, what we call as a X gate in the quantum computer. So you'll see very simply, if you apply a NOT gate to the qubit which is in a 0 state, right, it will reverse as a NOT gate does and force the qubit's state to become 1. And we can express this as before if, because it reverses, so if it was A ket 0 plus B ket 1, after the reversal it will become B ket 0 and A ket 1. So basically I'm showing the 0 and 1, but if this was in another state, it would become the reverse of it. So, and then the probability, as I just explained, the probabilities will also reverse here, right, when you measure. So when we measure this kind of a circuit, the result will be 1 with 100% probability. There's another important gate, and I'm just giving examples so that you understand there are some basic gates like we have in quantum computers. There's a gate which we call the H gate or the Hadamard gate. The property of the Hadamard gate is that if our qubit state is in 0, after applying a Hadamard gate, it will make the probabilities of the state equal. So if we apply this to, let's say, a 0 ket, we apply the Hadamard gate. After that, the state will become 1 upon under root 2, the amplitude, this will be the amplitude of get 0, 1 upon underscore 2, and it will fall on the equator somewhere. It could be anywhere because we are not concerned with the phase right now. And why this number 1 upon under root 2? Because if you square this number, it will give us the probability of 1 by 2. So there is an equal chance that after measurement, this qubit will either become 0 or 1. So this is, so you can say by manipulating how these probabilities will turn out when we make the final measurement, we can we can increase the chances of the result, or we can get to know the chances that the result that we expect when we have implemented an algorithm on the qubits, it will give us a high probability of what the result will be. So this is also called the phenomena of quantum randomness. So H gate will always cause qubits to start in a random state. So in many programs, especially in machine learning, because I think many of you will be familiar with machine learning, we always start with setting up our initial state in a random state. So similarly, in the quantum computer, we generally start by applying Hadamard gates to our qubits so that they're in a random state. And then we apply the algorithm and try to solve the problem and see what is the probability of the answer. What is the most probable answer that is coming? And that's how we solve the problem. So I hope you're getting the notion here. So I'll just stop here in case there are any questions for a minute. So I'm just going to the Q&A channel. Would you be covering the basics of quantum computing, which I am? The phase, I think I answered this one, Sharad. Could you please let me know if any collaboration is possible? Okay, we can come to that later. I mean, if a quantum computing, can I break the code of a locker? Yes, you can break. With quantum computers, we can break a lot of cryptography. Yes, I will be coming to superposition. Okay. So, so now let's just move on. I'll come to superposition and all the essential ideas around it. So Chiranjeev, after this section, I'll cover the questions. So I just want to leave you with the thought of appreciation that how is it that we say that quantum computer can process better and more states of information than a classical computer. So now we know that a qubit has two state dimensions, 0 and 1, and that too through the A and B complex numbers, actually we can represent any point on that sphere. So this is the state of how one qubit does. And if we compare it with the bit, it's holding two components or two dimensions of information at the same time. So with one qubit, we can actually hold two quantum states. Okay. Now, if you look at two qubits, if we have two qubits in our state, then what happens is each qubit can have 0 and 1 at any point in time. So if you look at the state in entirety, there are four quantum state dimensions here. So 0, 0, 0, 1, 1, 0, 1, 1. And now you know that two qubits can actually hold four quantum states because these 0, 0, 0, 1, 1, 0, 0, 1, 1. These are the four quantum states in this particular implementation of a quantum computer, let's say, which just has two qubits. So now the amplitudes of the states are represented by A, B, C, D, and if we square these amplitudes, it will be on measurement, what will be the probability that this particular state will collapse into A squared, B squared, C squared, D squared. Four probabilities will come. These probabilities may be 0 or it could be any positive number. But the important thing is that the sum of these probabilities will be equal to 1. Okay. So now depending on these probabilities, we will know at the end for this 2 qubit system, what will be the final state. So similarly, if we keep increasing the number of qubits in our system, which is now we are moving towards more and more powerful implementations of a quantum computer, then with 3 qubits, we can hold 8 qubit states of information. So that is a lot more information. So similarly, if you keep expanding it, there's an exponential growth in the number of information that can be represented as the number of quantum state increases. It's 2 raised to the power n. So with 10 qubits, just with 10 qubits, we can actually have 1024 units of information. Whereas if you looked at this on a 10-bit classical computer, you know that at any point in time it would represent only uh, 10 into 2, 20 kind of information. So like this, it is increasing. And finally, if we keep expanding on it, we are able to realize exponentially more. If we only have 275 bits, we'll actually have more state dimensions to this quantum state than we have number of atoms in the entire universe. So I hope this helps you appreciate the exponential power. So how do we put this to use? So imagine you have a caffeine molecule. Why is caffeine molecule important? Is it just, that it is involved in chemical processes. When we consume it in our brain, it makes us more alert. So of course, there's a lot of research around it in the medical area, that how can we extract the medicinal properties of this and maybe use it for the better of humanity. Anyway, so the challenge with these kind of problems, especially with these molecule kind of problems, is that the energy configuration of a molecule is very complex. It depends on the kind of chemical bonds which are between the different atoms, their orientation, the vibration, the speed of the atoms. So at any point in state, simulating the energy configuration of any molecule, especially as the size of the molecule increases, becomes more and more complex. And that is why research is very limited in this field, because classical computers cannot enable us to simulate all kind of energy configurations with so much degrees of freedom. So then what happens is, what happens in the nature, in life sciences, biology, chemistry, etc., is we always take approximations. We know in existence from experiments and observations what is the likely energy configuration, and that's how we work on it. We do not explore all possible simulations of the energy configuration, because it's not practically possible, and this limits us in our acceleration of discovery of new compounds for healthcare, material sciences, energy creation options, etc. However, now if we just took the example of a caffeine molecule, on a classical computer, we would need 10 raised to the power 48 bits to represent the energy configuration of this molecule at any point in time on a classical computer. That is too much of requirement for a classical computer. And and this is actually equal to 1/10 of the total number of atoms that we have, like just to give you the analogy. But if we had to represent the same molecules energy configuration on a quantum computer, realize that state, we could do that with just 160 qubits, right? So like this, if we have thousands of qubits in a quantum computer, which is something which we will look at what is the capacity we are working with today, then we can actually chart out the complete molecular configuration with much more accuracy, and then do experiments on it for discovery. So instead of doing experiments for years and years in the lab, you could actually simulate on the computer what is the art of possible, how can we use it, how can we combine it, what kind of reactions are possible that reduce the total energy state of any kind of chemical reaction, and therefore it is possible. So these kind of possibilities is what excites us about the field of quantum computing. And this can be applied in other business areas also. We look at some of them. So now we are going to go into the properties of quantum computing. What are the essential ideas that we use? And before I do that, I'll just see if there are any further questions that came up. Can we use quantum computing in astrophysics? Yes. So we can use it for any kind of problems, and we look at some of the examples. 2-bit in classical bit versus 2-bit, the number of states are same. So what is the difference of advantages? I don't know, like this is what I try to cover, Abhi sir. 2 bits is 1 and 0. Qubit will have a has a state in which it can have 0 and 1 at the same time. Okay, let me give you a different analogy. Let's say you toss a coin. So when you toss a coin, when it goes up, when it is up in the air, you really don't know whether it's 0 and 1. And we say this is like it exists in 0 and 1 at the same time. It's only when it comes down and we observe, we know whether it was 1, the final result is 1 or 0. But while it was up in the air and it was existing in multiple states at the same time, the similar way, the qubit, as I say, it will be in existence in any combination of amplitude of 0 and 1, and it's only when we measure it, it will collapse into 0 and 1. So while it is in that state, in the quantum state, when it is, in a state of energy mixed, if you superimpose it and entangle it with different qubits, then you get a lot of ability to express a state dimension which is much more than just 2 bits. So that is where the difference lies. So I think after going through some of these ideas, it will become more clear. We will cover the use of quantum computing in financial markets. Is any correlation? Okay, I'll just park the questions. Open 2 questions. Could you cover any correlation between quantum computing and blockchain? There's no correlation per se, but yes, we can design solutions using both the technologies together, but we will not cover that today in this session. Okay, let's come to the next topic, which is essential ideas, which I think everybody is waiting for. So mathematics, we need to just go back to the mathematics. So mathematically, we can use linear algebra to actually represent the quantum state. So the zero-ket state is represented as a complex space vector with 1 at the 0th position. And similarly, the 1-ket is represented with 1 at the first position, right? So this is just the way we have decided that we will keep these, the computational basis of a quantum computer. And we can write any vector which is of this form in this linear combination, right? So A ket 0 plus B ket 1. Now these are called the computational basis. So 0 and 1 is actually called the computational basis of a quantum computer. So basic unit, like you have 0 and 1 in the classical computer. So now we'll try to understand what is superposition then. Superposition is creating a quantum state that is a combination of 0 and 1. Like on the sphere, any point, we say that because it's a combination of 0-ket and 1-ket, which are 2 extreme states, when we have a qubit in a state where it can exist together or in a combination of 0 and 1, that is what we call as the superposition state. And the constraint in this is that A and B are complex numbers, and A square plus B square will always be equal to 1, because this represents the probability, and the probability of any state, as you know, is always equal to 1. So with this constraint, what we can say is that now if we just put any number, like this could be any kind of amplitude or any kind of constant, in any case, when you will come up with the probabilities, it will always be equal to 1. So this is just something that we need to understand. Okay. So, so superposition, if you look at it on the sphere, is any point on this particular sphere is when you're creating a quantum state. These conditions is what is allowing us, and we call this kind of a sphere a block sphere. You'll hear this a lot if you read about the quantum computing for literature. And A and B, another constraint is they always have to be non-zero. Okay. Now, if they're non-zero, that means that they're in superposition. However, if one of them is 0, they're not in superposition, they're in the collapse state. Okay. So because they're in a combination of 0 and 1, this is also, you'll hear a lot if you read about it, that a qubit can be in 0 and 1 at the same time. This is the mystery around it, because everybody starts thinking, how can they be in in 0 and 1 at the same time. How can anything be like that? So this is from the idea from quantum mechanics, where we know that, for example, a particle can be a wave and a matter at the same time, right? It can exhibit the matter properties and wave properties at the same time. So similarly, the notion of a qubit is it can be 0 and 1 at the same time. And I just explained you how, and how we mathematically model this aspect. Now, the other important aspect was measurement, which I think I've already explained. In this particular aspect, and I see we have 25 minutes, so I'll be trying to go through this section in lesser detail. So measurement is forcing the qubit state A get 0 plus B get 1 by observing it. Measurement means observation. So whenever we observe it, we will actually have it fall and collapse into certain definitive probabilities of 0 and 1. For example, uh, you know, equal probability of becoming 0 and 1 will be when we have this kind of an amplitude. This is an amplitude which represents 75% chance of being in the 0 state after measurement. So basically, the act of measurement enables us to come up with the probabilities that what is the result likely, what is the result that the state was in so much with so much amplitude in 0 1 and so much amplitude in 0 in state 0. So that is how the measurement collapses it, and that's when we make the measurement and the state is actually destroyed after that. The other property that we need to understand is that we can actually entangle two qubits. So this is just a chip, and we'll look at the chip designs later. But let's say we have a quantum chip, like we have a semiconductor on a classical computer. So entanglement is when we have a combination of two or more qubits and they're entangled with each other in a combination. So this is an example where we say that 0 is the state of the first qubit and 1 is the state of the second qubit. Like the second element is the state of the second qubit. So 0 1, for example, 0 1 ket will mean that the first qubit is 0 and the second qubit is 1. And because this is becoming one state now after entanglement, the amplitude squared of all these state dimensions will result into 1. And from here, we also know that what do we actually mean by entanglement. So this is, you have combined them together, okay. But how do we know whether they're entangled or not? Because they just may be sitting in a combination without actually getting entangled. Entangled is a state when we cannot separate two qubits from each other because they're combined in a very unique manner. Now, what is that manner? So now just imagine mathematically, you can actually write a state and it doesn't have to have probability. Some of the probabilities may be 0. So in this case, let's assume some two probabilities are 0 and we are left with this kind of a state with a 2 qubit state. And what we can actually do is we can separate out the first qubit and write it like this, get 0, and rest is of the portion remains. So if we can do this, we can actually separate out a qubit. Once we have the final state measured, it actually means it is not entangled because they can be separated. However, let's say we are left with a state which is 0 0 1 1. So in this case, there's no linear way in which you can actually separate out one qubit, because if you separate it out, it should have the same value, either 0 or 1, at the same position in both the state dimensions. So now it is not possible, and this kind of a phenomena is called that the states exist in entanglement. So once you measure, the property of entanglement is that once you measure even one state, you can predict what that other state can be. So for example, if you measure this and you find that with a 1 by 2 probability, 50% probability, your state is 0, the first qubit is in 0 state, the second qubit is in 0 state, then you know automatically that the other state dimension will be 1 1, right? So this is how we actually exploit this property a lot. So just to give you some more examples, this is not entangled, right? Because you can actually pull out 0 1, but both these states are entangled because there's no way in which you can separate the two qubits mathematically, and of course physically it will destroy the state if you try to do that. Now we use actually these kind of properties to cause a phenomena known as interference, which I will tell you in a while. So quantum computer, as I told you, uses these ideas. So then we come to the notion that we try to combine and entangle all these qubits using gates such as this. This is actually an entangling gate. Then there are gates uh, which are single qubit gates, like Hadamard we discussed about it. We use them, and this is just an example of a circuit. And all these circuits are actually reversible. What it really means is that if we apply this the same gate the next time, you can actually reverse the operation. For example, I said that the H gate will cause you to move the state into having a equal probability to be on the equator, right? But if I apply two gates, it will again reverse the operation and cause the state to collapse back into one. So all quantum gates are reversible, which is different than classical. Classical gates may or may not be reversible. So I'll move on. So the property used by superposition and entangled is interference. And interference is very much like you have in physics, you may have studied that there are different waves. And if you have two different waves, then depending on the frequencies of these waves, they may either kind of uh, cause a probability to change. So the final state when you combine both these waves will change. Your amplitudes may increase at some places and your amplitudes may decrease. So if I just talk in terms of quantum, you may have probabilities getting, your amplitudes may be increasing and decreasing. And by doing this phenomena, like it's called coherence and decoherence. So decoherence will cause your amplitudes to actually reduce on certain state dimensions where the results are not desirable, and increase in certain dimensions where the results are desirable. So interference is used. It allows us to increase the probability of getting the right answer and decrease the probability of getting the wrong answer. So like this, all quantum operations and problems that we solve are probabilistic in nature, and we kind of leverage these ideas of causing superposition, entangling the qubits together, and then causing some interference by an external source driven by the algorithm to increase the propensity of getting the right answer. And that's how we go about solving problems on a quantum computer. So this is just illustrating how it would happen as we are applying different kind of amplitudes. And how we apply this is by using some technique by which we can alter the state of the qubit. So I'll just again look at the questions. Entanglement is 2D. Can it be 3D? It can be any number of dimensions depending on the total number of qubits in the state, right? You can also entangle 3 qubits together. Please share what this is all about. Can you explain once again how we require less qubits compared to classical bit logics? Okay. Sharad, I'll come back to you. It's all exponential. So basically, if you have any bit can represent only one state of an information, but a qubit can represent 2 raised to the power n states of information. So if you have n bits, it represents n states of information. If you have n qubits, it represents 2 raised to the power n states of information. That's as simple as it gets. Okay, so I'll move on now. Now we are going to look into, we got to understand like what are the basic principles by which qubits operate, but how do we realize a qubit? How is a qubit actually formed? So qubit type properties are found naturally at an subatomic level, right? In the particles like bosons, fermions, etc. They all exhibit these properties in nature, and this is what the quantum mechanics is all about. That when it comes to actually realizing these in real world on the quantum computer, there are different systems or materials using which we can simulate quantum behaviors. So like iron taps, we can use photons, we can use topological nanowires and all. So I'll just give you an example of superconducting qubits. And this is an example of a chip from IBM, where you can see the superconducting qubit is realized on a chip, silicon chip like this, where there are 4 qubits, and these are the 4 qubits which are pointing out, and we use a particular invention called a transmon qubit, which is a qubit in which the noise is suppressed to a good extent. I mean, that is good enough. So how do we realize such a such a superconducting qubit? So as you know, there are some properties like aluminium, etc., which displays superconductivity behavior, and this behavior only exists on low temperatures where there are Cooper pairs formed, and you can read about it because we wouldn't have time about it. But we take two wafers of the superconducting aluminium and we insert an insulator in between. And what this does is this helps us in changing the potential energy of this particular system, this particular joint. So superconductors will always, with very low resistance, for a long, long time, they will keep giving a complete flow of energy, like flow of electricity. However, if you bring in an insulator, it disrupts the potential energy structure of the entire unit, and it creates a difference in energy at the in the energy flow. And we actually exploit this to say that this energy state G is called the ground state or the zero ket state, and this particular elevated energy state is called the E state or the one state. And we don't bother about these, but all our microelectronics is then focused on trying to control these two states, manipulate the qubit or this particular unit by the flow of pulses at different frequencies and for different duration. We try to control the flow and try to cause these two different states to come in existence. And this is actually realized on a chip. It's called a Josephson junction, and this is realized, and this is just a big you can say version of it, how it actually this works on the bit. These are all the control electronics by which we kind of send the microwave pulses at a certain frequency to manipulate the flow of energy at a particular phase angle. And that's how we control and we realize the same behaviors that we just talked about on a computer. So this is going from the physical part to the actual the realization in terms of computation. So as you can see, this is an example of another qubit on a chip. These are all the resonators. Resonators are doing nothing. They just manage the frequency at which, the energy will be sent to manipulate these qubits. So here we have like 5 qubits, and there are different resonators to kind of apply entanglement between two qubits. So you saw the entanglement gates, which I said was a controlled gate. And there could be individual gates by which we are just sending energy to put a qubit in a certain state. And using this complex electronics is how we use it. And because this is also at superconducting temperature, we need to keep it in a dilution refrigerator, which is realized by having a very, very low temperature close to absolute zero. And this is how we actually manage the entire, we place this chip actually in this dilution refrigerator. Now there is techniques of doing this. Here what we do is, if we mix helium, which is liquid helium and liquid and another isotope of helium at a certain temperature, as the two isotopes mix, heat is observed, and what is left is they become very cold and allow us to realize temperatures which are close to like 15 millikelvin or something, where we place this. Here now they'll be displaying the superconducting behavior, and by managing the microwave pulse duration, which is a form of energy, we will manipulate the qubit. So all this control electronics allows us to realize a quantum computer. This is how a quantum computer actually looks like. There are input lines by which we are sending energy through microwave pulses. There are output lines from which we are doing the readout. There is a magnetic shield protection of the quantum chip, because we need to make sure the outside atmosphere, any kind of radiations that are not disturbing. We have to really protect this chip together. And these are all the control electronics which are managing the microwave pulses and all that. So now if I just show a small video to you how it actually works. So from we'll program, let me just stop this. We'll program from a computer actually how through normal programming, Pythonic programming only, we are going to send some kind of algorithm will be executed, which will be sending some information to this control electronics panel, which will change our digital signal into microwave pulses at a certain frequency for a certain duration. And I'll just play the video. And these will be, actually going into the dilution refrigerator in form of pulses, and they will operate and perform whatever algorithm we need to perform, and the results are calculated by observing the state. So we do a readout again, which is again in the form of the pulses that the readout is done. This data is transferred back through the control electronics, changed into a digital signal, and we get the result out. So this is how we actually realize a implementation. So now the question comes is, at what state are we in terms of our maturity with the quantum computers? So in 2019 at IBM, there was a 27 qubit computer which came out, which is very less. We talked about, for realizing a caffeine molecule, for example, we need 160 qubits. So definitely, to solve bigger problem, we need to have hundreds and thousands of qubits on the quantum computer. But as you saw the complexity of the control electronics, it is not so easy to realize it. That too, and keep it at such a small temperature, like less temperature of absolute zero. So what is actually happening is, every year there is advancements, not just by IBM but even outside IBM, Google. A lot of startups are coming up with different type of qubits. Doesn't have to be superconductor qubits based quantum computers, but a lot of research is on to see how do we do it. From IBM's standpoint, we are actually more than 1,000 qubits per machine right now, and there is inventions and R&D happening on how we can increase it, and so far we seem to be on track to realize 4,000 qubit by 2025. Similarly, on the software side, we are coming up with new assembly, similar to assembly language on classical computers. There is a own kernel that can work with all the control electronics and control the hardware, actually, to help them execute the algorithm. Then we have different packages for algorithm, which is the software which typically we all would be learning to work with quantum computers. And it's like a serverless implementation, so that it becomes very easy for us to work without touching the hardware electronics, and then more sophisticated applications on top of it. So that's how the roadmap is laid out. So very easily we can say within 5 to 15 years is the horizon that we look at, is when we will realize quantum computers which can be put to solve large scale problems. Even now, using combinations of hybrid and classical, we can actually realize a lot of use cases and benefits, and we'll look at some of them. So just coming from a perspective that what could you do today, or how is it easier? Do you really need to know all this to work with a quantum computer? It's not like that. So developers using classical can also use quantum. They can use the same tools, same languages, same kind of code to program on a quantum computer. So we have different levels of, complexity though. Kernel developers are the ones who work on creating high performance circuits, who understand the controls, the pulse and timing controls that need to be used, and they write actually programming. They do programming to control all that electronics. So those are the kernel developers. Then the more abstract level is the algorithm developers, who know how the kernel works, and they write building blocks on top of it for preparing the states of the qubit, for enabling the operators and coming up with the logical gates, and to help construct algorithms. And then we have these model developers, equivalent to what you would say a data scientist in machine learning. What they know is, they know how the building blocks are programmatically. They use them to create circuits and algorithms, so that other developers can actually describe their problem and focus on the solution, while a lot of the complexity is abstracted. So this is very similar to, like, you in machine learning, you have your own scientific packages, like you could have TensorFlow implementation. Right now, you can use the TensorFlow implementation and solve a problem, and what goes behind it is not something which is abstracted for you, right? Because you've become a user. So this is the kind of frameworks which the model developers would typically provide. And this is equivalent to application developers or data science in AI. And these are, of course, writing, like actually writing a AI framework. This would be like assembly level code developers or people who are writing CUDA optimization algorithms, etc. So just abstracting it. And typically, the way we use quantum computers today is we use a combination where we are solving a big problem, but parts of it is still executed classically. Parts of it where we need to realize the problem in a higher state dimension, we put them on the quantum computer, those problems, and try to see what is the probability of getting a certain state after certain computation. And that is how we bring that result back. We take it back on a quantum computer and then we continue with the processing. So maybe in another session, I can tell you about more how we realize this to have the notion of quantum neural networks today, where it uses the optimization is done using classically, but the state preparation and the feature engineering is done on a quantum side. So there is a combination how this happens. And this is just how it happens. You write a quantum program, it's queued up from a runtime on some kind of a platform, similar to like you could have your Kubernetes platform in machine learning. There'll be an open platform on which there will be some interpreter which will take the job from the queue, convert it into the assembly code, execute it on quantum hardware, and return the result back. So now let's talk about the applications, and maybe I'll need 5 minutes more because this is also important. So there are three general areas in which quantum applications reside today. So one is simulating quantum systems, which are actually showing quantum behavior in nature. How can we simulate it? And we looked at the caffeine example, right? So that just, you can imagine that in quantum chemistry, discovery of new materials in material science, and realizing quantum physical states, all these are good application areas. In AI, we use it for better model training, pattern recognition, fraud detection, because now we can increase the state dimensionality, and the kind of features that are expressed on a quantum computer can augment what we find using the classical computer using machine learning. So there is a lot of application in very mature packages now in AI space. And another class of problems is on optimization or Monte Carlo type of models, which are probabilistic in nature. So for realizing it, because we can simulate a lot of situations given the high state preparation with certain probabilities, it lends itself very well to solving these kind of problems like scoring with a lot of variables for loans and credits, risk analysis, portfolio optimization. So if we just talk about it, these are a lot of the other examples. So we can talk about improving battery materials, drug discovery, protein structures, then how we can do more of chemical product design. When we talk about AI, we use it a lot for fraud detection, portfolio management, asset scoring, airline scheduling problems. Anywhere where you think it is very complicated, too many number of variables exist, and we are not able to express on a classical computer the problem. We are always have to do a constrained implementation by selecting a few features. So in these kind of cases, we can actually use some techniques to bring in quantum into the picture to solve the problems. And this is a lot of it is in experimental phase. As the number of qubits that can sit on a quantum computer increases, then our ability to solve some of these problems is only going to increase. Similarly, for optimization problems around product portfolio optimization, vehicle routing, etc. So we'll look at some of the examples in the next few minutes. So where we are working with a lot of industry clients in these kind of problems is in, as we just said, like complex data processing, search and optimization, simulating nature. These are some of the clients which are actually having their units, their own quantum teams, and they are doing a lot of research here. And we are actually working with a lot of these people like Boeing, Energy, Goldman Sachs is a bank, HSBC. So all of them have their own quantum divisions where they're doing a lot of experiment research on the present day quantum computers. So for example, we are doing trading simulations such as derivative pricing, which can improve the outcomes predicted from the financial instruments. And another one is perform complex scenario simulations in various cases, because many times we take assumptions and the estimation accuracy is actually curtailed because of the approximations we need to take on a classical computer. So these are some places. The other one is on find better patterns within AI/ML processes, because as I said, the data, the structures are you know hard to express on a bit system versus a qubit system. So we always have to take some optimization and reduce the accuracy. But on the quantum computer, we can overcome some of these barriers even now. So for just for example, we worked with Mercedes-Benz on for material discovery and manufacturing optimization. So if you know, there is a lithium sulfur rechargeable battery, right? The problem with that battery is that how do we improve the performance, make it work with lower energy and improve the performance. And for that, there are a lot of ways in which we can introduce catalysts, etc., to make the battery performance better. So for doing that, we are actually working with Mercedes-Benz. And then as a tool for chemistry and engineering with petrochemical companies. Then again, for routing, so for optimization, we have this problem where there are almost 500 LNG ships which are taking transporting critical fuel supplies across the oceans to destination ports. And the problem is that how do we, given the weather patterns, given different geopolitical situations and everything, how do we make these thousands of journeys more efficiently and come up with an optimal route structure? So this has a lot of variables, and in order to solve this problem in real time, right? Because day to day you need to change the routes and take look at the weather patterns and make changes. So so this cannot be done actually on a classical computer with as much accuracy as we think we will be able to solve it using a quantum computer. So this is a complex optimization problem, just an example of it. And similarly for financial industry, so somebody asked that question. So here, if you look at and I'm going to take 5 minutes more, we have this quantum computer being used using quantum machine learning, where we model a Black-Scholes model. That's a well-known model actually, which is used for derivative pricing. And it works again on probabilities, random setup, and then coming up with the probabilities of the best asset class, like the spot price of an asset, basically. And and it models like a most risky asset and a least risky asset, and then there is some kind of a modeling. There's a complex formula around it. So here, what we do is we simulate on the quantum computer a generative adversarial network, which many of you with the ML background would know. And on this quantum computer, what we do is we try to get the probability distribution from the GAN and then serve it into another quantum amplitude estimation algorithm. And what this does is it helps us in predicting the expected payoff with time. This kind of a simulation is very difficult to do on a classical computer. So these are some of the areas where it is done. Again, for detection and analysis of the Higgs boson also, we can use quantum. So this is a physics application, and there are a lot of more. So I'll just take 2 minutes to tell you a little about what you can do as practitioners to learn about quantum. So we have actually open access. At least IBM offers all quantum computers publicly for free over the cloud. And not all, there are premier users also, but you can get very good, at least for learning and for experimenting your problems, you can get free access through the tool. And all the code which is written, the Qiskit library which we have used, that is open source. It's available. It's written in Python. It's open on GitHub. So you can go and learn there. So all software tools and frameworks are available to the whole world. Anybody can go and leverage them. And there is also a lot of free educational resources, which we'll take a look at. So we talked about Qiskit, which is the open source SDK for programming quantum computers. So actually, there are different layers, as you know. The one is a simulator layer, using which you don't actually have to, you can use a simulator to model your quantum behavior instead of using the actual quantum computer. But there are also hardware providers, and we just don't have IBM computers. There are also integrations with other companies which are providing quantum hardware, and this may not be semiconductor based, it may be some other implementation. Then we have core capability. So this is a core, you can say core package. But then we have high level applications which typically practitioners would use to solve problems in machine learning, finance, nature means chemistry, physics, etc. Optimization. So the different packages built where a lot of algorithms are already implemented. What you need to do is learn how to state your problem, on use which algorithm to use, how to convert your data on in terms of a quantum convert it into quantum form so that you can actually solve your problem on a quantum computer. And there are low level applications also available on source. Let's say you want to start designing a new chip. So Qiskit Metal is actually allowing people with advanced knowledge to do such kind of things and run experiments on Qiskit. There are a lot of resources at every level for new learners, high schoolers. We have hackathons. There are internship programs. There is a whole Qiskit ecosystem on Slack. There's a Qiskit channel using which all enthusiasts can discuss with each other how they're using Qiskit and IBM Quantum to solve any kind of problems. There are programs for graduates and independent learners. There are Medium channels. We hold the global summer school every year, which has like more than 5,000 odd people joining in. And in 2 weeks, we try to teach a lot around the quantum, Qiskit basically, quantum computers and Qiskit. And then PhDs and working there are teach the researcher seminars. Again, this is all available freely to all educational institutes. Classroom learning platforms are there where you can actually design your own curriculum to teach the students. So there is a lot of traction now happening. Every year we see more and more people, students and otherwise trying to learn about it. More than 6 million learners have been leveraging these educational platforms. And we have, like IBM has invested more than 100 million just in supporting quantum education. So there is a lot. What you can do is there's an open source Qiskit textbook that can be read. There are there is a org, qiskit.org. You can go there and look at the learning resources. You can also go through some of the tutorials if you want to learn more about Qiskit. Then there is also certification that IBM offers in case you want to get certified as a developer. There is a Qiskit YouTube channel which gives a lot of good materials to learn. So this is a course which we recommend to people. It started 1st of November last year. So you can actually see all these videos which give you the basics of understanding all about quantum. And then there are books written by different people on quantum, how to use quantum computers with Python, more about the qubits. So there are a lot of resources. And then there are quantum resources available on the cloud, like the IBM Quantum Lab, where you can even right now go and start experimenting. I don't have time to share all of these. And then there is a lot of research happening. You can see the acceleration by which research is happening, and a lot of this is using IBM Quantum and Qiskit. More than 2,100 papers have been published, which try to come up with some algorithms or solve some problems like fraud detection in financial markets, gravitational wave detection, composite optimization in different areas of business and science. So with this, I'll just see if there are any questions which have not been answered. Okay, so how can we use entanglement for communication? There's quantum communication. We haven't covered that topic, but yes, entanglement can be used for communication. That's a topic of quantum communication networks. India actually has a cell dedicated on doing this. I mean, we are doing great work in India around this at a research level. Raman Research Institute is actually doing this work, so you can check that up. We don't have time to talk about it, but yes, quantum communication is a different application of quantum, and you should definitely read more about it. Do you have examples to share in use of qubits in supercapacitors? I'm not clear. I get this question, so maybe you can write to me. Is there possibility of general purpose quantum computers If yes, how quantum computers can be maintained at. So I explained about this, right? The helium refrigerator, but the search for quantum computers or quantum phenomena which can be controlled at room temperatures is on. Though it is, we don't know whether that will ever happen or when it will happen. So till that time, as I explained about the dilution refrigerator, we keep it, and quantum computers will not be everywhere. Quantum computers are not going to replace classical computers. They will just be an alternative or complementary form of solving some problems. Like, you will not be using a quantum computer to design your website or normal applications. It is in special problems related to optimization, simulation of nature, or machine learning, etc. Really advanced levels is where quantum computers would typically be used. We talked about the use cases. So any other questions or thoughts? I'll just stop sharing now and we can see if there's anything else.
I think there's no more questions. I'm also able to see in chat. I think Sharad Bhargava has raised his hand. Okay, let me allow him to speak.
Yes, Sharad.
Could you please elaborate on the research which Mercedes-Benz had with IBM on that? How exactly you arrive at a energy configuration of a lithium phosphate, this one sulfate? It would be interesting, ma'am, because I am from
Okay.
Mercedes-Benz.
Okay, I can point you to the. I'll share with Vimlesh the papers. There are series of research papers that you can go through. But basically, the idea was that in order to lower the energy requirements required by sulfur lithium batteries, how can we go about researching that in an optimal manner? And we'll have to go through the research papers for some of these problems. But idea was, how can we simulate the energy configuration required, and what kind of catalyst options can be recommended by the quantum computer, so that the people who are doing research on it in labs, they can focus on certain molecules or certain properties which need to be taken care of to enable the lithium sulfur batteries to lower the energy consumption. So that was the whole idea about it. And there are at least there was a series of research papers, not one or two. So I can share. Actually, the slide had the link, so I will share the link with you, and you can read about that. Any other question?
That's all. There's one question from Rohit. This quantum computing needs cloud service or physical server to run. Is there any relation with cloud computing?
Okay. So, cloud computing. So, cloud computing is a general term. So, behind on the cloud, you can have your classical computer. You can also have a quantum computer. You will send your request in normal programming language. Behind the scenes, there is a runtime controller which will orchestrate what workload can be done classically, what needs to be going to a quantum computer. So such kind of software has been, you can say, already developed, as I showed you on the skit. So it is possible. So that's the relation with cloud computing, that the quantum computers are accessible via cloud, and you don't have to learn an entirely new language to be able to program on a quantum computer. You can try it out today. I mean, we don't have time in this session, but maybe if we have a future session, I can tell you how to actually go log in, access, and try to come up with simple programs by which you will be able to experience the power of a quantum computer. But if you go through the learning resources, you'll be able to follow that. So then the next question is, will we get the presentation? You will get some of the slides, definitely, which I can share, especially the educational resources and links and all that I will be sharing with Vimlesh to further cascade. What are the job titles, scope of work in quantum computing demand? There's a lot of demand. I mean, you could see the research is increasing. There is a lot of opportunities to hire people with good understanding about quantum computers to perform research, to develop further software, to work with all these organizations as they are going to set up more and more departments which are focused on quantum. But these jobs will not be like a Java developer or something, because there are very specific problems in which we will be using quantum, and the opportunities will increase in the coming decade, because as we build more and more powerful quantum computers to exploit the advantages, we will need more workforce. So definitely there'll be a lot of opportunities. um, any small project is there? Yeah, we work on a lot of projects. Like I do a lot of exploration on quantum machine learning in the fraud detection area. There are options. Okay, I think we're done. Then
Yes,
there
I
is
think
Sharath is again asking something.
Sharath has already. Sharath, is there anything to ask? You can unmute yourself. You can see a lot of people.
Yeah, just one question for my curiosity sake. As I mentioned, so there are some cryptography where, like for example, to predict an outcome, say password of say simple 4-bit, madam. So if I don't know the outcome, like what could be the probability of a password? Can I use any of the algorithm which better predicts this outcome? Okay, this is the password, because I don't think quantum computing without knowing the outcome with a likelihood or a more probability, you can estimate this answer accurately. Is my understanding correct?
Okay. So most of the algorithms that we have which encrypt your password, right? You don't know the password, that's fine. But the algorithm which encrypts your password, there is an algorithm which does that. And what it does is it will kind of use the properties of factorization to encrypt your particular password. So what quantum computer can do is it can there are algorithms which have been written on using quantum, which can do factorization very efficiently, which is not possible on the classical computer. So what they do is they will come up with, given your public key, they will come up with all the possible factors and give you the likely factor. Now this, if you use the same thing to do on a classical computer, it will take years and years, because the number of
Okay.
numbers that we multiply, those are very big numbers, right? So it will be like,
Okay.
let's say about 20 digits and all. So you can think you cannot factorize these numbers, but on a quantum computer, you can. And if you can do that, you can get the prime factors. The moment you get the prime factors, now you can use that to predict what is the, original numbers which were used. So you can break the encryption. So you don't need to know the password, but you can break the encryption and get the password really revealed. So this is actually a big problem. Like the moment the quantum computers reach a certain area that they can, using Shor's algorithm, you should check that algorithm out, they will be able to do factorization of very large numbers that will enable us to break the current day encryption algorithms very easily. That's how it works.
There is
Thank you,
one
ma'am.
more
Thank you.
question from Manoj. So, any TQ scholarship for the supporting the fees?
I didn't get what TQIP is.
So, Manoj, you can write to us if you have any more queries on that. So, we'll answer your queries. I think we can take a last question, Chandrasekhar. Can we simulate real world if we have a very big quantum computer?
I mean, it's an interesting question. We can simulate behaviors which occur in nature at a subatomic level on a quantum computer. As a quantum computer becomes big, like even we don't know how big will they become, and simulating real world is very vague. So we have to be specific in asking the question. But the thing is, can we simulate chemical reactions which happen in a lab, which we have no way of doing on a classical computer? Will we be able to simulate them on a quantum computer? Yes. Even today, for molecules which have only 2-3 atoms, like lithium hydride or things like that, we are able to simulate on a quantum computer, like how can reactions happen, what will be the lowest energy state. So those things can be simulated. Similarly, quantum mechanical, like the performance of, like what are the properties of subatomic particles for studying quantum mechanics that can be simulated on a quantum computer. So there are some applications, but yes, we have to wait for the evolution of quantum computer hardware to see what other things can be done.
Right. Manoj has mentioned it's PEQIP.
I don't know that term. Sorry, Manoj.
I think we are running out of the time. I think it's time to wind up the session. So first of all, thank you, Tripti, for taking out your time and giving us a very insightful session. And hopefully soon we'll plan a part 2 on this. And regarding the resources of the webinar, whatever materials what Tripti has used, and also webinar recording, so we'll be sharing in our Times Pro AI community. So I have just pasted our link in the chat, so you can just join our community, and soon we will be posting all the recording of this entire session. And once again, Tripti, thank you so much for taking out your time and giving us an insightful session. And I really thank all the learners taking out their time on this weekend and joining this insightful session. So, as a Times Pro, we would like to thank each one of you for taking out your time, and also Tripti. And hopefully, we will see you soon in the next week with the next event. So, till that, take care, be safe, have a great weekend.
Thank you. Thanks, everyone.